All right, everybody. Sorry I can't be here today. I'm at a conference about the new cast testing. So what I'm going to do is I made this video so that I can show you how to start the mass appeal worksheet. And so in this, what you're going to see is a bridging together of bringing both the mole ratio concepts we were working on a couple weeks ago and the mole conversion concepts we've been working on the past week. So we're going to use both of those ideas to answer what are called stoichiometry questions, where you're going to be given a chemical reaction and then you'll be asked to predict how many grams of a substance you'll make if you start out with a certain gram of another substance. For example, if I give you this chemical reaction up here for water, and I say, so how many grams of water can we make if we have 30 grams of hydrogen? So remember, the coefficients tell us the mole ratio, but they don't tell us anything. They don't give us a comparison for grams. So that's why we've had to do all these gram conversions. So what we're going to be doing is returning these grams into moles using the mole ratio up here, and then figuring out how many grams of water we can make from 30 grams of hydrogen. So that's the whole gist of this type of work. So let's see how this works. All right, so everybody should have this worksheet called Mass Appeal, and we're going to start on the front part of it. So first thing we need to do is fill in this molar mass chart right here. Okay, so hopefully you guys had a few minutes after your quiz in order to look up the molar masses for each of these substances. So remember, we find that on the periodic table, where we're going to, for example, for calcium iodide, we'll look up calcium and iodine and add them together. So 2 iodines plus 1 calcium. So when you do that, you should end up with 294 grams. Okay, this is the molar mass, which means it's grams in 1 mole. Similarly, with sodium oxalate, the second one, we're going to add up 2 NAs, 2 Cs, and 4 Os. And you should end up with 134 grams. Make sense so far? All right. So the third one, again, molar mass for calcium oxalate. We're going to add up 1 calcium, 2 carbons, and 4 oxygens, and we're going to end up with 128 grams. And then last but not least, we have sodium iodide. Now in the formula here, you've got a 2 out in front, and that is the number of moles that are needed in the recipe, right? But what our graph asks for is the molar mass, which is the grams in 1 mole. So all we have to do, or what we should do, is add up 1 sodium and 1 iodine together. And when you do that, you get 150 grams. So a lot of people may have 300 there, okay, because you did the 2 times that. But remember, in molar mass, it's the mass of 1 mole. All right, so we're going to use this molar mass in order to help fill in the rest of this table. So we see that we've got 4 experiments here that have been done with this reaction. The first one's all filled in for you, and it follows exactly what the recipe or the reaction says. There's 1 mole, just like we have a 1 up here for a coefficient, of calcium iodide, 1 mole of sodium oxalate, okay, matches that 1 in the reaction, 1 mole of calcium oxalate, which follows that, and 2 moles of sodium iodide, which again follows our recipe in our reaction. So if we convert these moles to grams, we get exactly what we see on the chart. Remember, 1 mole times the 294 is going to be 294 molar mass, or grams per mole, is just 294, right? So in 1 mole, we already said that sodium oxalate weighs 134 grams, so that's why it's right there. And then as well as the calcium oxalate, which is 128 grams in 1 mole. Now the only one that's changed from the top is the sodium iodide, and that's because, remember, we took our molar mass and we have 2 moles in our recipe, so 150 times 2 is why we've got 300 right there. Okay, so that's how we're getting all of these numbers. Now in the second experiment, we're going to be using the molar mass again, and along with the mole ratios in the actual reaction in order to help us fill in these missing blanks. So let's start over on the left-hand side with calcium iodide. All right, so we know that we have 147 grams of calcium iodide in this experiment. So we need to figure out how many moles that is. So remember from our mole island that to get from grams to moles, right, is just one conversion using our conversion factor. 1 mole equals whatever the molar mass on the periodic table is, right? Our grams from the periodic table. So to find our missing moles, we're going to take 147 grams, and we're going to go 1 mole of that is equal to 294 grams, right? Remember, we got that from up here. So 147 divided by 294 is a half a mole. So that's one way we could have solved for this, but there's actually a second way we could have solved for this. So let me actually write that in there before I forget. 0.5 moles. Okay, so there's a second way we can actually solve for this, and this is using one of our old tricks called the mole ratio. If we take a look at our coefficients for this reaction, we can see that for calcium oxide, we have a 1 mole, and for calcium oxide, we have 1 mole, and for sodium oxalate, we have 1 mole. So this is a 1-to-1 ratio between that guy and that guy, right? So whatever he is, he will be the same, okay? And the same for this one, because they're all, like, these 3 are all 1-to-1 ratios. So because we know that sodium oxalate is a half a mole, we can determine that our calcium iodide is a half a mole. And check it out, we can also determine this missing piece has to be a half a mole. Okay, so again, we used our mole ratios. Okay, so that's what we were doing a couple weeks ago. Mole ratios to go from one substance to another in terms of moles. Okay. All right, so that gives us our missing piece for sodium oxalate in the second column over, which is great because we can't get grams unless we have moles. All right, and so in order to find the missing grams for sodium oxalate, we'll take our, we're going to use our, mole ratio again, okay, for 1 mole equals whatever's on the periodic table. And this time, we're going to be multiplying. So 0.5 moles. To get rid of moles on the bottom, we'll be multiplying by our molar mass. And for this time, the molar mass for sodium oxalate is 134. So we're going to use that, 134 grams. So when we do that math, right, 0.5 times 134 is going to give us 67 grams. So this is our missing grams right here, 67 grams. Okay, and again, we got that from the moles. If we found the moles of sodium oxalate by using the mole ratios from the chemical reaction. Once we found moles, we can easily go to grams by multiplying by our molar mass. All right. So let's do a similar thing for the last blank here on the second, or the last column on the second experiment. So here we are given the fact that we have 150 grams of sodium iodide. Okay, and so we can see actually that matches the molar mass. So 150 is grams in 1 mole, so that must mean that we have 1 mole here. Okay, so it's 1 mole there. Make sense? All right, so this is the gist of how we're going to be solving these. So let's keep going with number 3. So in experiment number 3, we're given even less information. This time we're only given the amount of moles for sodium oxalate and the amount of moles for calcium oxalate. Everything else we have to figure out from those two. And so remember, up above, we figured out the moles of the missing ones by using the mole ratio. So if we take a look again at the mole ratio from sodium oxalate to calcium oxalate, it's a 1-to-1 ratio. So 1-to-1 ratio means that whatever one guy is, the other guy is. So if one of them's 0.1, then the other guy has to be 0.1. So this one here is 0.1 moles, or 0.10. There you go. Okay. All right, now if we take a look at the mole ratio between calcium oxalate and sodium iodide, we can see from the reaction that this is a 1-to-2 ratio. So that means whatever this guy is twice as much. So if the one on the left is 0.10, then the other guy's twice as much, 0.20. So that means we know that the moles for this one is 0.20 moles. Okay. So again, we're using our mole ratio concept from a couple of weeks ago. So now that we have the moles for everything, we can go and figure out grams, right? Very easily. So remember, if we have moles, we can go to grams by just multiplying our moles times the molar mass from the periodic table. Or in this case, it's what we have up top in our molar mass chart. So let's take a look at calcium iodide first. In calcium iodide, we have 0.10 moles. And remember, the molar mass is 294, so we can just do 0.1 times 294, which will give you 29.4 grams. So that's how many grams are in 0.1 moles of calcium iodide. So 29.4 goes right there. All right, similarly, for the next one over, sodium oxalate, again, we've got 0.10 moles of sodium oxalate. We're going to multiply that by our grams, okay, because remember this is grams in 1 mole. So we're going to multiply it by 134 grams in a mole. And we're going to end up with 13.4 grams. Makes sense? So if we do the same thing with the other one, we're going to do 0.1 times 128. That'll give you 12.8 grams. And then last but not least, here we've got, remember we have 0.20 grams of sodium iodide. So we want to do 0.2, I'm not grams, silly teacher, 0.2 moles of sodium iodide. So we want to multiply that by the molar mass, 150 grams, and that ends up being 30 grams. So 30 grams goes there. Okay, makes sense? All right, so we've done experiment number 3 as well. Now let's take a look at experiment number 4. Experiment number 4 is having you, it basically only gives you one thing to start with. It gives you 10 grams. That's it. That's all we know. We have 10 grams of calcium oxalate that was made, and we have to figure out all the other stuff. But because we know how to go from grams to moles using our mole island conversions or our formulas there, and then we can use the mole ratio in our reaction, okay, to get the moles of everything, and then we can go to grams of everything else that's missing. So it's 3 pretty easy steps. So let's take a look how this works. So because we start with just 10 grams of calcium oxalate, the only thing that we can actually do with this number is convert it to moles. Okay, so that's our first step. We're going to convert grams to moles, right, of our substance. So let's do that. So 10 grams of the calcium oxalate. We're going to convert it to moles by dividing by our molar mass that we've got above. So that's 128 grams. So when we do that, we're going to get 0, that's a weird 0, let's try that again, 0.078 moles. And so that's going to be our moles for calcium oxalate right up here, 0.078. Okay. All right, so that's a good start, and that's going to open the door to every other mole blank right here. Because remember, we can use mole ratios to figure out the other guys, okay, the moles of the other guys. So if calcium oxalate is 0.078, remember all of the reactants are 1-to-1 ratios. So that means this guy has to be 0.078. And this one also has to be 0.078. Make sense? Okay, so then the last one is sodium iodide. And remember, this one is a 1-to-2 ratio. So if, 1-to-2 ratio. So if this calcium oxalate is 0.078, then the other guy is twice as much, which is 0.0156. So this one would be 0.156 moles. All right, so with one number we've gotten so far. We've changed, we've converted grams to moles. Our second step was to use the mole ratios, right, to figure out the moles of every other reactant and product. And now our final step then is to convert the moles that we have to grams. Okay, so convert moles to grams. That's our third step. Okay, so for calcium iodide over here, we're going to take our 0.078, multiply that by our molar mass of 294, and we'll get 23 grams. So down here is 23 grams. Okay. We'll do the same thing with the guy next door. So 0.078 moles times 134 grams will give you 10.5 grams. And last but not least, over here on the product side, 0.156 times 150 is going to give you about 23.5 grams. So we can see that from just knowing one thing about our products or reactants, 1 gram value, we can figure out all the rest by putting together what we know about mole conversions and mole ratios. Okay, so these are the kinds of problems we're going to be working on the rest of the class period today and then all next class. We have lots of practice, and then all next week we're going to have labs associated with this where you're going to do these types of problems and see how much you can actually get in the lab. So it should be a pretty fun week ahead. Okay, so the only thing that I'd like to do, is to go over number 2 and 3 with you. So question number 2 says, is mass conserved in experiment number 1? So what it means is that is the mass the same on the reactant side and the product side, right? So is the law of conservation of matter being followed in this case? And so what we'd have to do is we'd have to add up the mass of the reactant side. So 294 plus 134 is going to give you 428. And then we add up the mass on the product side. So 300 plus 128, again, is 428. So you could say, yes, mass is conserved because the number of grams is equal on both sides, right? So we know that the mass is conserved. But number 3 is asking, is the number of moles conserved? okay, in experiment number 2. And so we'll do the same thing. We'll add up the number of moles on the reactant side. So 1/2 plus 1/2 is 1 mole. And on the product side, we have 1/2 plus 1 is 1.5 moles. Okay, so this answer is no. Okay, the number of moles is unequal. And this is super important to realize because remember the mole ratio, or the coefficients in the reactants, in the reaction, I should say, is telling you the mole ratios. All right, and so it does not mean that the number of, it's not a ratio between grams. Likewise, the law of conservation of matter is basically only for mass. The mass is conserved, but the moles are going to be off because moles is, relative to how much there is, okay, and what types of atoms and elements are there. All right, so your job is to finish up as much of this worksheet as possible. So keep going with the questions on the first page, and then on the back side is another chart just like this one. So you're going to use the same exact steps that we used using the mole ratios and mole conversions to fill that in. All right, we'll see you next class.